Morning students, in the last class we have just discussed about electrode potentials, that is how to write the cell representation, what about the anode and what about the cathode, then what about the cell potential, how to write it for a general case. Now I will take one example for the corresponding to write the cell representation and all. So for example, for the cell reaction, Cu solid plus Ag plus aqueous giving rise to Cu2 plus aqueous plus 2Ag solid. So here first identify which is undergoing oxidation and which is undergoing reduction. So here copper is undergoing oxidation and Ag is undergoing reduction. Okay. So here half cell reactions are written as at anode half cell reaction will be Cu solid giving rise to Cu2 plus aqueous plus 2 electrons, that is oxidation reaction occurs. Now at cathode Ag plus aqueous plus electron giving rise to Ag solid. So 2 is introduced to balance the equation. Now cell representation. So at anode, at cathode there will be reduction reaction taking place. Cell representation can be written as, first you write the anode, that is Cu solid bar Cu plus 2 aqueous double bar Ag plus aqueous single bar Ag solid. This is anode and this is cathode. Okay. So this is the way to write the cell representation. Now next is to write E cell. E cell is equal to E right minus E left, that is equal to E Cu plus 2 bar Cu minus E right is Ag plus bar Ag minus E Cu plus 2 bar Cu. So here we are writing the reduction potentials for the every metals. Now I will solve one or two problems related to this concept. First one, problems. First one, calculate the EMF of the cell. Calculate, 2 marks question it is. Calculate the EMF of the cell. Calculate the EMF of the cell prepared by the combination of Zn bar ZnSO4 1m and Cu bar 1m CuSO4 at 298 Kelvin. Given E0 Zn is equal to minus 0.76 volt and E0 Cu is equal to plus 0.34 volt. So here they are given. So how to identify the values? First I will tell you. In the problem, if you are given the value, one negative and one positive, then negative value is selected as anode and positive value is selected as cathode. Okay. So here both the values are positive. Then positive with lower value, that is value lower, is selected as anode and positive with the higher value is selected as cathode. And if they are both are negative, then more negative is taken as, that is more negative in the sense higher value, higher number with more negative value is selected as anode and lesser negative, so that is lower number is selected as cathode. So here this is the way to represent anode and cathode in the given cells. So here they are given the values of E0, Zn and E0, C. Okay. Now EMF of the cell. So E0 cell is equal to E0 right minus E0 left. So here which is right, which is anode? E0 Cu is having positive value, so that it is taken as cathode, and E0 Zn is having negative value 0.0676 volt. It is taken as anode. Okay. So here E right means first to write the E0 Cu minus E0 Zn, that is equal to point plus 0.34 minus of minus 0.76, totally 1.1 volts. 2 marks question, formula 1 marks, then answer plus unit 1 marks. Second question, again 2 marks. Second question, calculate the EMF of the cell. Calculate the EMF of the cell. Calculate the EMF of the cell consisting of standard reduction potential or standard electrodes of metal with SRP, that is standard reduction potential, are minus 2.38 volt and minus 0.76 volt. So here it is again a 2 marks question. First write it as M1 and M2. Take first one as M1, second one as M2, which is anode and which is cathode. So take it as E0 M1 is equal to minus 2.38 volts. This is taken as anode, and E0 M2 is equal to minus 0.76. This is selected as cathode. So in the problem you are asked to calculate EMF of the cell, so E0 cell is equal to E0 right minus E0 left, or cathode minus anode. So E0 right is minus 0.76 minus of minus 2.38. Totally it is 1.62 volt. Okay. Third question. A galvanic cell is represented as galvanic cell is represented as M1 solid bar, M1 N plus aqueous double bar, M2 N plus aqueous single bar, M2 solid. Write half cell reactions and overall cell reaction for the above cell. It is for 3 marks, half cell reactions and overall cell reactions for above cell. So here, in order to write half cell reactions, so here it is anode and it is cathode. So first write the half cell reactions. At anode reaction will be, write down this one, M1 solid giving rise to M1 N plus aqueous plus N electrons, that is oxidation is taking place at the M1, and at the anode, at the cathode cell reaction M2 N plus aqueous plus N electrons giving rise to M2 solid is the reduction taking place at the cathode. Okay. Now overall cell reaction can be written as overall cell reaction. So just you add the 2 reactions, M1 solid plus M2 N plus aqueous giving rise to M1 N plus aqueous plus M2 solid. So here I will end the problems. Now next part is measurement of electrode potential. So next part, measurement of electrode potential. Measurement of electrode potential. So galvanic cell is a combination of two half cells, okay? One anode and another cathode. Individual half cell cannot work independent. It has to work in the presence of another half cell. So here, if I calculate or if I give you a electrode with unknown electrode potential and ask to calculate, then we need another half cell that is having value which is fixed, and this half cell with fixed value, fixed electrode potential is called as reference electrode, and generally we select the reference electrode as the standard hydrogen electrode. That is, for reference electrode we select the standard hydrogen electrode, that is SHE, or it is also called as normal hydrogen electrode, NHE. And for this standard hydrogen electrode, cell potential EH2 bar H2 bar H plus is equal to 0.0 volt with the cell representation PT solid bar H2 gaseous bar H plus aqueous. So here H2 bar gaseous is at 1 bar pressure, and H plus aqueous is of 1 m solution of HCl. So here cell representation for the standard hydrogen electrode, important. Standard hydrogen electrode, it is called as SHE, or normal hydrogen electrode NHE. It has got the electrode potential that is 0.0 volt, and cell representation PT solid in equilibrium with or H2 gaseous bar H2 aqueous, H plus aqueous. And with the cell reaction, H plus aqueous plus 1 electron giving rise to half H2 gaseous. So with the cell reaction, H plus aqueous plus 1 electron giving rise to half H2 gaseous. Now here definition of standard electrode potential or standard hydrogen electrode. It is a standard hydrogen. It is an electrode at a or pure hydrogen gas at a high temperature of 1 bar pressure. Definition of SHE. It is an electrode. It is an electrode in which pure hydrogen gas at a pressure of 1 bar is in contact with H plus ions of 1 mHCl at a temperature of 25 degree in presence of platinum. So in presence of platinum at 25 degrees. So here it is an electrode in which pure hydrogen gas at a pressure of 1 bar is in contact with H plus ions of 1 mHCl solution in presence of PET platinum at 25 degrees. The setup for standard hydrogen electrode will be like this. take down the experimental setup for the standard hydrogen electrode. So here pure hydrogen gas at 1 bar pressure, then pure and dry hydrogen gas. This is wire for external. So here there is mercury and it is platinum foil. Okay, this is Hg, this is platinum wire, this is platinum foil, platinized, and this is 1m HCl solution, and here I will write this is Cu wire for external circuit. Cu wire for external circuit. Then it is Hg, platinum wire, finely divided, platinized, that is platinum foil platinized, and here this is 1m HCl. So unabsorbed gas will be bubbling. Unabsorbed gas will be bubbling through the solution. So this is the simple experimental setup for standard hydrogen electrode. Here we have a platinum electrode, that is platinized platinum electrode. Platinum electrode is a platinum foil coated with platinum black. So here we are coating it with the platinum black in order to increase the absorption power of hydrogen gas. Okay. Now this platinum foil is connected with a platinum wire and it is placed in a glass case with mercury, and for the external circuit copper wire is placed for the external circuit. Then it has got another glass jacket, outer glass jacket, and this outer glass jacket has got an opening from which pure and dry hydrogen gas is passed at a pressure of 1 bar pressure. Okay, and the platinum electrode is just immersed in 1m HCl solution, that is 1 molar HCl solution. Now when pure and dry hydrogen gas is passed at 1 bar pressure, the outer jacket is in contact with the hydrogen gas. Okay, now the platinum foil will be coming in contact with the H plus ions of 1m HCl and it will absorb hydrogen gas. Okay, the gas is passed until there will be bubbling, continuous bubbling from the openings of the platinum foil. So that here the standard hydrogen electrode is going to act as both anode as well as cathode required by the condition. So here oxidized and reduced forms, of hydrogen remain unity in the standard hydrogen electrode. That is concentration of HCl taken, HCl solution, that is H plus ions, is of 1 molar, and pressure of hydrogen gas passed is 1. Okay, under these conditions this standard hydrogen electrode will show a cell potential of 0 to 0.0 volts. So by this reason we are using this as anode or this as cathode. Suppose if the cell is or given electrode is calculation of electrode potential of unknown electrode, calculation of electrode potential of unknown electrode. So you see here given electrode that is M1, given electrode M1 is taken as anode, then SHG is taken as cathode. So set up the cell as per this condition. Here M1 is that, okay, and here SHA, that is experimental setup of hydrogen electrode is that, and you connect the external circuit by the connections. So here right hand side electrode is cathode is SHA and left hand side electrode is M1. Now in here cell representation can be written as at M1 metal is undergoing oxidation, so then write the oxidation reaction M1 N plus aqueous double line H plus of 1M bar half H2 gaseous bar PT solid. Okay. Now EMF of the cell is given by E right minus E left. E right is E naught H2 bar H plus minus E naught of M1 bar M1 N plus. Okay. So here E naught has, because E naught H plus bar H2 or H2 bar H plus bar H2 is 0.0 volt. So it is simply E M1 bar M1 N plus bar M1 can be written as minus E cell. So this is how in the Daniell cell we are calculating the EMF of zinc as Zn is equal to minus 0.76 volt. Okay. So in the second case, first case is given electrode is anode. In that case, SHA can be taken as the cathode. Now, in the reverse the case, that is given electrode is cathode. In that second one, given electrode is cathode. So that SHA acts as anode. Given electrode say M2 is taken as cathode. So set up the cell with standard hydrogen electrode at the SHA at the anode and M2 at the cathode. Okay. M2 at the cathode. So connect the cell by external circuit. Now in this case cell representation can be written as PT solid bar H2 gaseous bar H plus aqueous double bar M2 N plus aqueous bar M2 solid. So here for this we are writing the E cell is equal to E right minus E left. So here E right is M2 N plus bar M2 minus E SHE. So that E SHE is again 0. So E M2 N plus bar M2 is equal to E cell. In the way we can calculate the EMF of copper Cu plus 2 bar Cu as 0.34 volts. So this is the method to calculate the electrode potential using standard hydrogen electrode. Now applications of standard electrode potentials. Applications of standard electrode potentials. Applications of standard electrode potentials. So for that I require one chart. So here first I will write reaction, that is oxidized form plus N electrons giving rise to reduced form. Okay. And lastly E naught in volts. So here first reaction will be F2 plus 2 electrons giving rise to 2F minus. So 2.87. Then Ag plus 1 electron giving rise to Ag solid with the electrode potential 0.80. Then Cu2 plus 2 electrons giving rise to Cu solid with the plus 0.34 volts. Then 2H plus aqueous plus 2 electrons giving rise to H2, half H2 gaseous with the 0.0 volt. Then Fe 2 plus 2 electrons giving rise to Fe solid minus 0.44. So Zn plus 2 electrons giving rise to Zn solid minus 0.76. Then Al 3 plus 3 electrons giving rise to Al solid minus 1.66. Lastly, there are some elements Li plus electrons giving rise to Li solid minus 3.05 volt. Okay. So here I have taken the decreasing order of electrode potential. That is, electrode potential of the element goes on decreasing. Here some properties are there. So different electrodes have got different electrode potentials. Okay. So first one, different electrodes will have different electrode potential, some with negative sign and some with positive sign. So some above the series are of positive sign and below hydrogen all are of negative sign. Now the second property is electrode with the negative electrode potential. Electrode with the negative electrode potential has oxidation tendency so that it undergoes oxidation easily, so that acts as strong reducing agent, oxidation agent. Or electrode with negative electrode potential has got oxidation tendency and acting as strong reducing agent. Okay. So here in the example, here I have taken lithium has negative lithium metal, lithium solid is taken as strong reducing agent because it has got most negative electrode potential. Okay, from the diagram, lithium solid is having most negative electrode potential of minus 3.05 volts, so that it is a strong reducing agent. Okay. Third property, electrodes with the positive electrode potential or greater than 0, here less than 0 electrode potential have got lesser oxidation tendency, but they show reduction tendency more, so that they act as strong oxidizing agents. Okay. So in the series, F2 gaseous has got highest or positive electrode potential, so that it is observed that F2 is going to act as strong oxidizing agent. Okay. Then fourth property, as we go down from top to bottom, what is the trend observed? Electrode potential decreases, so that oxidizing power of the substance oxidizing power of the substance decreases and hence reducing power of the substance increases. Okay. Now next property, that is next application of this electrode potential is nothing but, there are another three properties. Just I will explain that one. So after this, next fifth property will be the electrodes with negative electrode potential or less than zero electrode potential when placed in dilute acid solutions, they liberate hydrogen gases. Okay, so that the metals like Mg, Fe and Zn will liberate hydrogen gas from the solution, whereas the metals like copper, then Ag, Au will not liberate hydrogen from the solution. Now next property, the metal with lesser electrode potential, that is negative electrode potential metals, will displace those with positive electrode potential. So here zinc can displace copper, but copper cannot displace zinc. Similarly, Fe can displace Ag, but Ag cannot displace Fe, like this. And the metals with negative electrode potentials are highly reactive in nature. As the electrode potential increases, reactivity goes on decreasing, so that electrode potentials with positive electrode potentials are nobler in nature. So these are the important applications of electrode potential. In the next class, we will discuss Nernst equation. Thank you.